Okay, so this last video here, we want to talk about interpreting integrals involving motion on a line. So a couple important things here for an object moving on a line with velocity v, which equals v of t in function notation. The net displacement of an object at motion that begins at time a and ends at time b is just the definite integral of velocity. That gives you the net displacement. That's kind of like if you take 7 steps forward and 3 steps back, your net displacement is 4 because you're 4 units where you started from. If you take the definite integral of the absolute value of velocity, you're going to get the total distance traveled over that interval, which is different than displacement. So if I take 7 steps forward and 3 steps back, even though I'm 4 steps from where I started, my total distance traveled would be 10 steps. So if the velocity is positive, this is a third little nubby here, on that interval, then the displacement is equal to the total distance. Because think about it, if velocity is not negative, if it's positive or zero, all that movement is forward. So you're not backtracking at all. So up to this point, we have several different functions we've been dealing with. The position function, which is s of t, the velocity, which is the derivative, or s prime of t, speed, which is the magnitude or absolute value of velocity. So velocity is a little more descriptive because it tells you not only how fast you're going, but which direction. And then acceleration is the second derivative of position or the derivative of velocity. So remember, speed and velocity are not the same thing, however. Even though they're very closely related, speed measures how fast an object is moving, regardless of whether it's moving forward, backward, up, down. But velocity, like I said, tells you both how fast it's going, the speed, and the direction. So because of that, velocity can be positive, negative, or zero. So let's look at an example here, number 10. And I put this in here because the definite integral of the absolute value of velocity is not equal to the absolute value of the definite integral of velocity. They mean two different things. The first one, your basically, if you have a function and it's positive, negative, zero on an interval, when you take the absolute value of it, it's essentially going to make all the negative values positive, which is going to act as if all the velocity is moving forward or in the positive direction, so that when you take the definite integral of that, you would get all positives and you would get the total distance traveled. If you take the absolute value of the definite integral, so then you would um, anti-differentiate, plug in, get your answer, then take the absolute value. That is not the same thing. Okay, so let's look at an example to kind of put this all together. An object is moving along a horizontal line with velocity v of t, inches or in meters per minute, from 0 to 6 minutes. Find the net displacement of the object from 0 to 6. Interpret the results in the context. Find the total distance traveled. So for part A, the net displacement is just the integral from 0 to 6 of v of t dt, which is the integral from 0 to 6 of 3t squared minus 18t plus 15. So we just anti-differentiate. So you have t cubed minus 9t squared plus 15t evaluated at 0 and 6. So if we plug in 6, you would have 6 cubed minus 9 times 6 squared plus 15 times 6 minus the function evaluated at 0, which is going to be 0. So all of this ends up being negative 18. All right, so what this means is that after moving from 0 to 6 minutes, the object is 18 meters. So we could put units on it because this is in the context. It's 18 meters to the left of where it was when it started. So for part B, if we want to do the total distance traveled, that's going to be the integral from 0 to 6 of the absolute value of v of t dt, not dx dt. Well, in order to do this, we have to figure out where the velocity is positive and where it's negative. So if we take the velocity function, 3t squared minus 18t plus 15. And then we factor it, you would have 3 times t minus 1 times t minus 5. Okay. Then we find out that the velocity, you could do a sign chart here. Here's 1, here's 5. And if you pick values in between, like if you pick 0, you would have 3 times -1 times -5, which would be positive. If you pick, let's say, 2, you would have 3 times 1 times -3, which means the velocity is going to be negative. If you pick a number bigger than 5, let's say 6, you'd have 3 times 5 times 1, which is positive. So we know that the interval from 0 to 1, the velocity is positive. The interval from 1 to 5, the velocity is negative. And the interval from 5 to 6, the velocity is positive again. So what we would do is simply do the integral from 0 to 1 of v of t dt. Then take the opposite of the integral from 1 to 5 of v of t dt, and then add the integral from 5 to 6 of v of t dt. The reason we do this one as the opposite, and I specifically said opposite and not subtract, is because on that interval, the velocity is negative. So if I integrate that and evaluate the definite integral from 1 to 5, the answer is going to be negative. So if I essentially subtract it or take the opposite of it, it's going to end up making it positive. So for the sake of time, I'm just going to evaluate all of this, and you would end up with 7 for this one, -32 for this one, but we're subtracting it, and then 7 for this one, and you'd end up with 46. So what this means is that from time 0 to 6 minutes, the object traveled a total distance of 46 meters. Alrighty? So another way to do this is you can use your graphing calculator or Desmos. I'm going to model this on Desmos. So what you could do is plug the function into Desmos, v of t, 3t squared minus 18t plus 15. And you could see that from 0 to 6, it's positive between 0 and 1. Then it's negative, and then from until 5, and then from 5 to 6, it's positive again. To get the net distance, you could do the integral. Just type in int, and then you put your limits 0, 6, hit the overspace one time, and instead of retyping the whole function, just do v of t, and then type in dt, and it'll give you -18. Okay. Now I'm just going to copy that and put it right here and insert absolute value symbols around the v of t, and that's going to give us 46. Okay, which is the answer that we got. Now, if I graph the absolute value of v of t, notice that essentially what the absolute value of the velocity function does is it flips all the negative, it reflects the negative part of the graph over the y-axis to make it all positive. So whenever you integrate the absolute value, everything is counted as positive movement, and you get positive 46. With the definite integral, we're getting net displacement. And notice the region that's below the x-axis is a lot bigger. Let me turn this off. In the red one, the original. Notice the region down here is a lot bigger than this little sliver here. And then if we just go to 6, it would just be a little sliver almost looking like a triangle. So it's going to more than offset the positive movement. So that's why our displacement ends up being negative. All right. So again, it's important to know how to do this both ways, and where things are coming from. So don't just feel like you can just do everything in Desmos and not have to worry about any of the analytical stuff we did here. All right, guys, that's it. Hope that was helpful to you. Take care.